Hello everyone and welcome to this lecture about the difference between classical mechanics and quantum mechanics. I'm so glad to see that so many people showed up today. Anyhow, this lecture will take a while, so let's get comfortable and start with something simple. Now maybe simple like addition and other basic operations. If you take one apple and add another one to it, then you get 2 apples. If you add yet another one, you get 3. If you add another 2, you will get 5, and so on. This is addition, and I will use it as a starting point in order to explain how quantum mechanics works. Because you see, if you take these summed up apples, then you can multiply them together. Multiplication tells you how many times you have to add something together in order to get the multiplied result. For example, you can multiply 5 by 2, or 5 by 4, or 5 by 10, or 5 by 600, the idea is the same. Now next we have exponents, or in other words, the same logic except this time for multiplication. So exponents tell you how many times you have to multiply something. We really often like to use dimensions in order to visualize exponents, but this usually limits us to only 3 powers. Here's an alternative way to think about them. I'll replace apples with icospheres for the sake of rendering all of these animations in just 1 week, because it's gonna be a lot. If you take 5 for example, then bringing it to the 5th power would mean multiplying 1 by 5, then multiplying by 5 a second time, then a third time, then a 4th time, and then finally by 5 the 5th time, which results in 3125, or in other words, quite a lot. Now that we know the basic operations, it's time to talk about... Let's start the simple stuff, like a 1 or a 2 or a 3. If we put all numbers on a line going like this, then we end up with a number line. Now this is incredibly convenient because it allows us to visualize things way more easily. For example, if you start right here with a 4, then you can add 2 to it and move it right. Or you can take 3 for example and add a 5 to it. Or you can take 1 and add another 1. But one thing which is really interesting is that no matter what you add together, you always move right, never left. So what if you want to move left? Well, let's examine this a bit more closely. Now it will get a bit cramped, but just stick with me here. We'll start with a blue point, to which we will add a yellow point, and we will get a red point in return. I know it is not as clear as we would all like it to be, but it will have to do. And here's also an arrow which will clear up absolutely nothing. I'll give you a second to take it all in, because now it's time for me to move around a bit. So if we move these points around, there is one really interesting thing we can see. The arrow attached to the ball always points to the right, never to the left. So what do we do now? Well, nothing. It seems like it is impossible for us to combine any 2 numbers and end up with an arrow that's going left. That's how any reasonable person would end this argument, but we're not here to be reasonable. We're here to do math. So let's take another closer look at this problem. You see, if we freeze the first point in place and just move around the second one, it would seem like the lower the number gets, the closer the arrow gets to pointing left. So what if, and just hear me out here, what if we were to add an additional number line, this time left from the 0? Well then, if we put the second point onto the other side, congratulations, we got the arrow to point left. Now that's something that really often gets underappreciated, just how weird and bizarre negative numbers are. But that's how these things get done in math, and that's how new math is invented. As long as something works and helps you solve a problem, it doesn't really have to make sense. So let's revise it for a second just to make sure that we all understand how this works. First we start with the problem. Then, if in our current model there is no way to solve that problem, we have two choices. One, give up and just assume that the problem is impossible, or reinvent the model and add something new that seems ridiculous but in reality could help you solve it. Now, reinventing the model will always seem like absolute nonsense, because what we're basically saying is, hey, remember that math thing that we all did and seems to be working perfectly fine? Well, how about we change it? But it doesn't matter, because feeling of making sense and making sense are two different things, which is a perfect way to segue into the second problem on our list of two problems. Let's imagine that we want to take some number x and square it, and get a negative number in return. How could we achieve that? Well, if you take a closer look at our extended number line, you will see that if we start at the red point and square it in order to get a blue point, no matter where we place the red point, the blue point will always be above 0. Always. So how can we bring the blue point to the negative side? Now, once again, we're faced with the exact same problem. And once again, there is a simple way to fix this problem. Just add more numbers. This time, instead of extending the number line to the left, we'll add another number line, the imaginary number line. So now if you take the I, which is the imaginary number, I mean I stands for imaginary, you get it, I don't know why I feel the need to explain it, and square it, then you will get -1. That's the definition for negative numbers. It's just the square root of -1 is I. That's the entire thing. Yeah, that's the whole definition. I'm glad I have an entire separate chapter just about this. -1 square root, that's cool, great. And there we go. That's the explanation for imaginary numbers. That's the reason behind them. You see, you can have 2 apples or 3 apples. That's basic, that's not that weird. But you can't have -7 or 7 imaginary apples, because these numbers aren't made to represent the quantity of things in real life. They were created to support maths. That's why they exist, not as the numbers stand alone by themselves, only as mathematical tools to describe other things. And right here is where most imaginary numbers explanations would end. But we can't have that yet, because you see, every single reasonable explanation requires 2 parts. First of all, why something makes sense, and second of all, why it's useful. And so far from what I've shown you, it seems like imaginary numbers, well, kind of make sense, but why would they be useful? Just I times I equals -1? What good does that do? Imaginary numbers are all about rotation. Now, from the explanation I've provided so far, it might seem weird, because the only thing that's defining imaginary numbers is I multiplied by I equals -1. So how could this help us describe rotation? Well, let's bring up our complex plane. That's the real number line and the imaginary number line. Together, they are called a complex plane. I should have mentioned that. And let's start with a 1. Now, let's take a look at what happens when you multiply this 1 by I, the imaginary number. The dot goes from here to here, because 1 multiplied by I is I. Now, let's take I and let's multiply it by another I. We already know that I times I is equal to -1. That's the definition. Now we can multiply it by I and get -1I. And if we multiply that by I yet again, we get -I multiplied by I. Or in other words, we get -1 multiplied by I multiplied by I. Or in other words, we get -1 multiplied by -1. Or in other words, we get a 1. And there we go. We are already rotating it around the origin. But I have something that's even better. Let's imagine an equation like this. E to the power theta I. Yeah, I know, new letter E and fucking Greek alphabet, but it is simple. E is just a number. I could extend it to 2.7182881826023745266249775724724709369995. But that unfortunately wouldn't fit in the animation, so I thought that E might be a bit better. But when it comes to theta, the Greek letter, it's just a placeholder. It's meant to be just a character representing a different value. If it's making you uncomfortable, I can just replace it with a smiley face if you want. Now, this equation is wonderful when it comes to explaining how imaginary numbers impact rotations. I'll use this dot right here to represent what this equation is equal to, and also will slowly increase the value of the smiley face. Now, take a look at what happens. We get a perfect circle rotation. That's why imaginary numbers are so important. Without imaginary numbers, you can't describe rotations all that well. With imaginary numbers, you can describe them perfectly. And the thing about maths is, when you unlock a new tool, you not only unlock this tool, you also unlock every single thing connected to this tool. So with imaginary numbers, you can solve not only rotation, but also angles, circles, oscillations, waves, this will be important later, and all the other things derived from those. Take a look at the sine function, for example. Extremely useful, extremely famous, appears everywhere. But if you take a look at its origins, then you will see that it originates from a circle and is used to describe rotation. So where's the I? Well, let me show you something that you might have not seen before. The mathematical definition of sine using just 3 aforementioned basic operations. Or in other words, this. We found the i's. So yes, even though the basic idea for why imaginary numbers exist is, well, basic, it's just I times I equals -1, that's the entire thing, their implementations cannot be underestimated. They are extremely useful. So functions. Now for functions, we'll have to start with equations. We are all familiar with some sort of equations, like for example, 1 + 1 = 2. There we go, that's an equation. Or 2 × 3 = 6. That's also an equation. Or for example,
2y minus 3y minus py x squared minus plus y times y divided by 3 multiplied by y.
It's easy. Now you may obviously say something like, make it claiming that these equations are easy isn't quite exactly all that accurate. I mean, yeah, the first one, sure, that was easy, but the third one, have you seen the third one? I suppose that's How can that be easy? The third one does seem to be a bit more difficult, but it's not. And in order to understand why, we'll have to talk about toughness versus complexity. Complexity and toughness are two very different terms which people really often tend to mistake. It's not that hard for me to come up with a complex problem and tough problem, but when it comes to solving these problems, for toughness you need intelligence, whilst for complexity you need speed. And that's actually kind of it. Let's take a look back at this equation. It's my very own, extremely old Boat-Fender equation. If you take a closer look, you'll notice that even though it's not that small, it's easy. Really easy. I mean, well, addition, division, you could solve it yourself if you want to. Now let's take a look at something that's actually hard. I'm shooting myself in the foot a bit with this, but the Gaussian integral. It's an extremely hard problem. So hard, in fact, I won't be able to explain it here. I'd recommend 3Blue1Brown's video, why pi is in the normal distribution, but you might have seen this animation meme before, showcasing step by step how to solve this integral. But here's the incredibly important, really often overlooked thing when it comes to this integral. This integral is not difficult because it's an integral, it's not difficult because it uses some funky notation, and it is not difficult because it takes a lot of steps in order to solve. No, this integral is difficult because it requires a lot of creativity in order to solve it. Taking the integral, bringing up from 2 dimensions to 3, then switching the coordinates to polar, then treating it like cylinders with the distance, that's creative, that's intelligent, that is new, that's why it's hard. So I guess that would be the main lesson of this video. When it comes to problems, don't judge them by just how large they are or just by how complex they are. No, The only thing that matters when it comes to problems is how difficult they are. And the only way to actually check if a problem is difficult or not for you is to try to solve it. I know it's not all that pleasing of an explanation, but that is the truth. People really often like to use these quantum mechanical equations, like this, for example, will be like, oh my goodness, that's so crazy difficult. But it's not. It's complex. There's just a lot of things going on, and scientists which like to use some notation that looks weird, whilst in reality this is actually pretty simple. So I guess that will be the main point of this video. All of these things aren't that difficult, and if you actually want to explain quantum physics, you can do it in just a single video, from addition to this. Anyway, what were we talking about? Oh yeah, right.
So let's take this equation for example. The only reason I'm picking this is it has a lot of different operations, so I think that it would be nice. It's 4 plus 3 divided by 2 times 6 squared. Cool. Now, if we change the 4 to 5, then the result changes. That much is obvious. We added 1 to this, so we get a result which is also 1 higher. Simple. Now let's add 1 to this 2 right here. We do it and we get a number that's smaller. That's weird. We added a number, but the result is smaller. We should take a closer look, and for that we should check it for more numbers. We should check what we get for a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, and a 10. Alright, that's pointless, too many numbers. We need a different, more graphical approach. Let's go back to our number line and let's add another one. This time it won't be the imaginary axis, only the result axis. So here's how this will work. We'll take 1, for example. We'll take the 1, we will input it right here into the equation, and we will add another dot representing the result. Now we'll repeat this for 2. Take the 2, input it into the equation, and note it down. Now 3, input, result, output. We can keep on going and just adding more numbers. There we go. This shows us pretty well what the function is all about. But if you want this to be even clearer, you can connect the dots. There we go. This graph right here tells you exactly what happens to the equation. And the idea is for each number on the x-axis, you take it, you use it to replace the x in the equation, and you bring it up to the height equal to y. Now, what's really neat is that we can repeat this process for every single number in our equation. And you can see how replacing the 4 with x causes the function to just go up, replacing the 3 causes it to go up in a different way, replacing the 6 changes the shape, and replacing the exponent to does something that's even weirder. So that's what functions are all about telling us how the function changes based on a single number, changing it. And this would actually be a perfect segue for
calculus. Here's the thing about math. If we take a look at this graph, then we clearly can say how things are changing, right? I mean, you can clearly say that over here the function is going up, over here the function is going down, over here it's kind of flatlining, then going down. Yeah, we can say that. But when it comes to math, you really often need a number, a value, something that you can actually check the representation. If it's going up, how much is it going up? How long is it going up? Is it going up forever, or will it fall down again? When it comes to math, you need values. You need to be precise. You need to be mathematically precise, or in other words, perfect. Which means right now, we need to find a way to describe this change mathematically. How could we do it? Well, let's first start with slopes.
So slope is just a line at an angle. I feel like that's a solid enough definition for the purposes of this video. So now, here's what we want to achieve. We want to create a system in which a slope like this would give us a high value, because it's a high slope. A slope like this would give us a low value, because it's a low slope. A slope like this would give us 0, because there is no slope. And a slope like this would give us a negative value, because it goes the other way. So how would we do it? Well, let's start by adding some numbers. We'll start with 2 points, the point A and point B. Both of them would have some coordinates, the x-coordinate and the y-coordinate. I'll just move them around a bit so that everyone would get how they work, because I believe that graphically it makes more sense than explaining it. Now, 4 numbers is a bit much, so we can reduce them down to 2. Because if you think about it, moving points 5 units to the right would result in the same slope as moving both of them 5 units to the left, which means that we don't really care about their actual positions, only about their relative positions. Or in other words, we only care about how far away this point is from this point. So if we take their coordinates and just subtract them, we get this. And because numbers all by themselves are kind of hard to follow, we can represent this graphically with these 2 lines. Now here's where the fun begins, because you see, if you increase the height, the slope increases. If you decrease the height, the slope decreases. So that's already half of the equation. What's the other half? Well, that's simple. Width. If we increase the width, we get a lower slope. If we decrease it, we get a higher slope. So what we can do is just inverse it. So divide 1 by width. Now, if we multiply these 2 together, then we get a value which represents the slope. So the slope of any 2 points would be just the difference of their height divided by the difference of their widths. And considering that in this case we have the x-coordinate and y-coordinate, we can note it down as the difference of y divided by the difference of x. And so there we go. That is simple. If you have 2 points, then you can check the slope by just dividing this by this. Easy stuff. Except here's the issue. When you're talking about functions, then you're talking about change at a point. Not 2 points, 1 point, which is less. If we're talking about change, we want to talk about change at this exact spot. Not the spot next to it, not the spot behind it, only this exact spot, which brings us to a problem. How could we describe this with only 1 point? Well, that's actually extremely easy. All you have to do is just bring back the distance from this distance down to 0. Now the 2 points are actually overlapping, and it's not an illusion, they actually are overlapping. If you bring down the distance to 0, they actually are, 2 points are in the exact same spot. Mathematically, it's accurate, it's fine, it's perfect. The only issue is if the distance between them is 0, then you end up with 0 divided by 0. How do you solve that? Well, let's take a closer look at what we're basically doing over here. Since we define slope as the difference between 2 points, we start that definition. We reduce the number of points to 1, and then we calculate. But here's the thing, what if we try to do it the other way around? In order to get what that means, let's try it with an example. First, we'll consider a function. F of x is equal to x squared. Now, let's try it the flawed way first. So we start the point, let's say for example something like this one right here. Now what are the coordinates of this point? Well, the x, or the width, will be equal to x, and the y will be equal to the height, so x output to the function. So far all of this is not all that complex, but I still would like to pause to make sure that it all makes sense. Alright, we have this point which has coordinates of x and y. X is equal to x and y is equal to f of x. Cool. Now what about this other point? Well, the other point we can just define by an offset. And even though it sounds fancy, it just means that it will be an h further away than this point, and f of x plus h higher than this point. Now what is the slope created by these 2 points? Well, once again, the difference of heights divided by the difference of widths. There we go. That's the equation. Now we go to the second thing on our list, which is to reduce the 2 points into 1 point. The way to do it would be by replacing the h with 0. So after we replace h with 0, we get... Oh no, we get f of x minus f of x divided by 0, or in other words, 0 divided by 0. Once again, we have the same problem. That's why we need to be smart about this. That's why we'll have to rewind and try this again, but in a different way. Which means that we'll have to leave merging these points for later. For now, let's try to solve this. So f of x is equal to x squared, which means that we can replace these functions with what they mean, like this. Now next, we can try to simplify this a bit. So x plus h squared will be equal to x plus h times x plus h. So we multiply x by x by h by x, and h by h. In the end, we'll end up with this. Now, in this equation, we have x squared and negative x squared, so we can cancel them both out. Now we just end up with xh, xh, and h squared. Xh plus xh is equal to 2xh, and now we just need to divide all of them by h. There we go. We end up with 2x plus h. Now, after all calculations are said and done, what is h equal to? Well, obviously it's equal to 0, because once again, we reduce 2 points to 1. So we replaced h with 0 and we get 2x. So in this entire function, we can say with absolute certainty that at any point, slope is equal to 2x. But what does this mean exactly? Well, let's start on the left, right here. Here we can see that the function is going down, which means that the slope should be negative. And after we input the x, so negative 2.5, into the equation we get negative 5. Which means that at this very point, the function is going down at a slope of negative 5. If we move it to the right a bit, we can see that the function is still going down, but not as much. So if we once again input the x into the equation, we get negative 0.5. So still going down, but less than previously. Now right here, x is equal to 0. 0 times 2 is still 0, so the slope is not existent. And we can see that right here, it seems to be rather flat. Now on the positive side, the slope slowly rises. Now this, the function describing slope of a different function, is called derivative. And we use the dy divided by dx notation to note it down. So dy divided by dx of f of x is just the derivative of function f of x. So derivative of x squared is equal to 2x. And this way we can calculate instantaneous slope of any function and precisely describe just how much they are going up and down. Or in other words, just how much the function is changing. That's what I adore about calculus. And here's the thing, if you understand what I've said so far, then you pretty much understand the whole calculus. There's only one more thing left to mention, which is this, the integral. Integral has a reputation for being incredibly difficult, but in reality the concept is unbelievably simple. Take a look at this function. You want to know what the integral of this function would be equal to? The area. That is it. That's the entire thing. That's what the integral is. But what if you want to actually calculate this integral? Well then, all you have to do is, remember taking the derivative, the thing I just mentioned from the function, the derivative? Well, if you go back, then that's just taking the integral. If you understand derivatives, then you also understand integrals. Many people even often refer to integrals as anti-derivation, because it's just derivation going the other way. I think that sucks actually. I think the integrals should be called integrals and the derivatives should be called disintegration, but that's just me. I stole that joke, by the way. Now, I feel like there is still one more question to be answered when it comes to calculus, and that's, why would we ever need to know the exact slope at a single point? Well, let's consider an example like this. You have a car which is traveling with some velocity. How would we calculate this velocity? Well, normally the answer would be simple. Take the distance this car has traveled and divide it by the time it took it to travel. In this case, if, let's say, this car has traveled 16 meters in 4 seconds, then we know that the velocity is equal to 16 meters per 4 seconds. Or in other words, 4 meters per second. That's how we usually do it in classical mechanics. Why do I say usually? Well, it's because, as with everything, there is an asterisk, because this is not equal to the velocity. This is equal to the average velocity. What about the actual velocity at any moment? Well, let's rewind to the very beginning and let's stop the car mid-track. How quickly is it going at 2 seconds? In the exact instant 2 seconds have passed. Well, that's simple. After 2 seconds, in that instant, the car has traveled 0 meters in 0 seconds. I mean, we're talking about an instant, right? An instant. That's what an instant is. 0 seconds. So obviously the car has traveled 0 meters. It's an instant. Once again, we're faced with the exact same problem. And the way to solve it is with the derivative. That's what the derivative is. A change of y in relation to x. And that's what velocity is. A derivative of position in relation to time. Meters, so position, in relation to time. So seconds. Derivation is actually an extremely common operation. The problem is, it's a bit too common, don't you think? I mean, if you use derivation to calculate something as simple as velocity, then how is it possible that most people have never heard of it? Well, it's because of precision. The difference between velocity and average velocity is that whilst average velocity is imperfect, because it obviously gives you the average velocity over the period of time, it is easier to calculate. Derivatives are harder to calculate, and that's why most people don't use them, even though they give you the perfectly exact velocity at any point. This difficulty with precision increase will come up soon, but first... And so there we go, that was calculus explained in... I have no idea, I haven't edited yet. Now it's time for the last bit before quantum physics, which is probability. So, where should we begin? How about with the probability function? Let's imagine that we have a basketball and a basket, and we will throw the basketball forward with some random force. Now here's the question. What's the probability that the basketball will make it into the basket? If we throw the basketball with too little force, then we will miss. But give it too much juice and the ball goes flying. So what is the probability that the ball will make it in based on the force? Well, here's the thing. Because of turbulent flow of air, even if you were to throw the ball with the exact same force, it can sometimes go in and sometimes miss the shot. So here's what we can do. For each different force, we can sample different throws and get the probability that the ball will make it in. So for example, if you throw the ball really, really weak, it never goes in. If you throw it a bit stronger, it sometimes goes in, but mostly fails. If you throw it even stronger, it goes in more often. Throw it even stronger and almost always goes in. But be careful, go over the limit, and the ball will mostly fail. Now, based on these different measurements, we can create this. A function, which tells us the probability that the ball will make it in, based on the force of the throw. Now, I know that this might have been a lot, but that's the idea. This tells us the strength, and this tells us the success rate. Alright? Simple enough for now. So, we know that if we throw the ball with this force, this is the probability that it will make it in. If we throw it with this force, this is the probability that it will go in. And for this force, this is the probability. Simple enough. But here's the more fun question. Let's say that we pick a random force between here and here, just any random value. What is the new probability that it will make it in if we pick a random value for the force? That's a rather difficult question, so let's start with something easier. Let's say that we have only two possible scenarios. We either throw it with 1/3 of the maximum force or 2/3 of the maximum force. Now, if for 1/3 it will have a 25% chance and for 2/3 it will have a 32% chance, then if we pick these values at random, the total probability that the ball will make it in will be equal to 28.5%. Why? Well, it's because there are two possibilities. We have a 50-50% chance that we pick the first one and the 50% chance that we pick the second one. So the total probability is 50% chance that we have a 25% chance probability, and 50% chance that we'll have a 32% chance. So the total is equal to 28.5%. I know that it might have been a bit confusing, so once again, these 0.5s are here because we pick the force at random, either the first force or the second force. It's a 50-50. And then these forces have their own corresponding probability that the ball will make it in. Does that make sense now? No? Well, don't worry, because there is more examples to not make sense. Like, let's expand ours by adding one more possibility. So right now we have 3 possibilities. We can throw it with 1/4 of the force, 2/4, and 3/4. Now, each of these forces have their very own probability of the ball making it in. For the first one, it's 12%, for the second, it's a 50%, and for the third one, it's 17%. Now, what's the total probability of the ball making it in after we pick one of these 3 forces at random? Boy, that's a mouthful. Well, each of these forces has a 33% probability of getting picked. So, once again, we multiply these 33% by their corresponding probabilities, then we get 26%. That's the probability that the ball will make it in after we pick one of these 3 forces at random. Still, let's go once more, this time with 4 forces. We pick a random force, which means that each one of them has a 25% chance of getting picked. Now, here are the probabilities, and by now, you know the drill. Add them up, and we get 24.5%. Now, this process should make some more sense, or at least I hope so, because here's where it gets beautiful. Let's think about what all of this means graphically. In order to make it easier for the eyes, we'll roll back the example to the one with only 3. So we basically sum together the probability of each force getting picked by the probability of the ball going in. Now, what are these 2 values graphically? Well, the probability of the ball going in is just literally the height of the rectangle. That's simple enough because the function in the background is literally the function in which the height represents probability. So obviously, the height represents probability. Alright, 1/2 of the puzzle solved. Now, what is the probability of each force getting picked? This one is also simple enough. You see, the probability of any force getting picked is equal to 100%, because one force is always picked. Now, if all of them are equally probable, that means that each force has a probability of getting picked equal to 1 divided by the number of segments, which, as it just so happens, is exactly equal to the width of each rectangle. So that means that we can just replace this with height, which, as you remember, is equal to the function in the background. The width we can just replace with 1 divided by number of segments. I'll just note the number of segments down as n. There we go. Now there's one more thing we can do to clean this up, and that's to replace these sums with a single sum. Now, mathematically, this changes nothing. I cannot stress the nothing of it enough. It's only notation. It's just really often used in order to shorten the equation a bit, because if we go back to 4, this is shorter and more readable than this. So yeah, there we go. We made an equation, and one thing that's actually kind of cool is that with this equation, we can just slowly increase the number of segments from 4 to 5 to 6 to 7, 8, 9, 10, and so on. And at some point, we'll reach the exact area under the function. One pickle though, at what point will we reach this area? Well, that's the issue. We'll reach it only when the number of segments is infinite. Otherwise, if it's equal to something like 1,000, like in this case, we could always just zoom in and see the error. But if it's equal to infinity, it would truly be perfect. That's nice. One little problem, you see, a funny story. If you insert infinity into our equation, then we get 1 divided by infinity. Now, this all by itself is not that big of a problem as it seems. I mean, using just one quick limit, we can say that it approaches 0 with no paradoxes, well, relatively no paradoxes. But if it does actually approach 0, then After we multiply the result of the function by the 0, we get a 0, which means that this sum is just equal to 0 plus 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 0, and so on, infinite number of times. So how could we solve this problem? Well, we already have, because we already ended up with one paradoxical dead end like this before in the video. Remember derivatives? Over there we also had to divide 0 by 0. So in order to avoid a paradox, we instead divided dy by dx and just sidestepped the whole 0 problem. So what if we do the same thing here? And we say that instead of multiplying by 0, we multiply it by dx, which approaches 0, because width of these segments gets smaller and smaller. And there we go! We have a foolproof equation. Well, almost, because you see, in reality, in this case, we wouldn't really use the capital sigma notation, because we don't really know exactly how many things we want to add. I mean, it's approaching infinity, so we don't know the exact number. So instead of sigma, we'll probably use something different like this kind of funky curvy line. Basically, oh my goodness, that's an integral! And so there we go. That's how integrals are made. When a daddy integral and a mommy integral love each other very much, then what they... Okay, I'm sorry. I'm just really excited because if you understood at least most of what I said so far, that means that you just went from addition to calculus in 42 minutes. A journey which normally takes around 16 years. But yeah, calculus, probability, was kind of the last thing on our to-do list. So right now, you do actually understand everything. We went over basic operations, over basic numbers, over advanced numbers, over equations, over functions, over calculus, derivatives and integrals, over probability, which means now it is finally time to get to the last bit of this video. There we go. Now you should understand everything you need to understand in order to get into quantum mechanics. Now obviously I will not explain the whole field, that's way above my pay grade. But I will give you a sample of what it feels like to work with quantum mechanics. And this sample will look like this. Now, isn't that just a beautiful equation? It looks so advanced, so sci-fi. It looks like something that a main character in a movie would try to solve in order to crack time travel. But in reality, as you will soon realize, this equation would be way more familiar to you than you think, except it has a quantum mechanical twist to it. So, without any further ado, let's get into it. Starting with this, psi. That's the name of this symbol, psi. But in reality, the name of this thing in quantum mechanics is the wave function. Now, let's divide into two parts, wave and function. You are already familiar with functions and how they work, what they are. And this is just any normal old function. Yeah, I know, the notation would seem to suggest that it's some sort of bizarre craft, but no, just any normal function. It's just this. It's the exact same thing. Except quantum mechanics really likes to use this all very seemingly advanced notation. But yeah, that's all it is. Psi would be equal to just any function, right? Nothing weird going on there. Except for the return. Because you see, this function, whilst it does take in just any odd number, it returns a complex number. A complex number would be basically a plus bi. Now in this case, a and b are just random numbers, but I is the imaginary number, the number you
know pretty well. Now, why is this called a complex number? Well, remember the complex plane. Well, if you take this complex number and you were to try to put it on the complex plane, then these are just the coordinates. I mean, A would tell you how much to the right or the left you have to go, and BI would tell you how much up and down you would have to go. Because, you know, if you multiply something by I, then you go up or down. That's just it. So this complex number is just the real number summed up to with some imaginary number. But why are we using a complex number instead of just any random normal number? Well, it's because of the first part of this name, wave. It's a wave function. And if you recall me explaining imaginary numbers, then you'll remember how I mentioned that imaginary numbers help you solve angles, circles, and also waves. The reason for why we use imaginary numbers for waves is, well, let's just say that it would make this video about an hour longer, and I will make a whole separate video just about that. But that's all you have to remember for now. This function has to do with waves, and because of that, we need imaginary numbers in order to describe them. So, let's recap. When it comes to this, it's just a function which takes in a number and returns a complex number, or in other words, a real number and an imaginary number. I know it's a lot, but it should make sense if you just stop and think about it. So let's go on, and let's add this. An asterisk and another psi. What is this asterisk? Well, it's not convolution. It is a complex conjugate. Oh my goodness, it sounds amazing, doesn't it? Complex conjugate. So sci-fi again. But in reality, as always, it is incredibly simple. You see, what a complex conjugate does, it just takes the complex number and just flips the imaginary part. That is it. So remember when you had A plus BI? Well, if you take a complex conjugate of it, you get A minus BI. That is it. That's all complex conjugate does. It just flips the imaginary part from positive to negative. So, what does psi, complex conjugate of psi, give us? Why is that there? Well, let's see what happens if we do actually apply this. By the way, this is psi multiplied by the complex conjugate of psi. I should have mentioned that. Let's see what happens when we actually solve this equation. Well, psi gives us A plus BI. We already remember that. So, let's multiply A plus BI by, in brackets, A minus BI. What do we get? Well, first, A times A gives us A squared. Then A times BI gives us ABI. And then BI, but that's with a negative, so minus ABI. Then we have BI times A, which gives us once again ABI, this time is positive. And then we have I multiplied by negative I. That's the last thing. So we have A squared minus ABI plus ABI, which means these two cancel each other out. And then what we have is negative I squared, negative BI squared. I'm doing this from memory, alright? Now, what is negative BI squared? Well, let's think about it. What is I squared? Well, if you remember it from the definition, I times I equals negative 1, which means I squared in this case will be just negative 1. So we have negative 1 times b. Negatives cancel each other out, and because of that we just get plus b squared. A squared plus b squared. Now, this may seem just extremely convoluted for absolutely no reason, but there is a reason. You see, on the beginning, from our psi function, we got a complex number, so a real number and an imaginary number. Now, after performing this operation, we get two squares of real numbers, or in other words, a positive number. So even though these functions can output any number in existence, you know, positive, negative, imaginary, real, any number, after we apply a multiplication by a complex conjugate, we get a positive number, a real positive number every single time. I'll leave it up on the screen for a second just so that you can actually take all of this in. Alright, everything clear? No? Well, then I would really suggest rewinding, because here we get into fun stuff, because here we get into probability. Why do we care about this function returning a positive number? Well, it's because you can't work with probability with negative numbers. You can't have negative probability. And so here's the thing, after we take psi complex conjugate psi, what we get is the probability function. Probability function of what? Well, a probability function of finding an atom in any place. Well, not an atom, a particle. So here's the idea. You take this function for any particle and you input a position into it. And then this function tells you what is the probability of this particle being in that position. That's already extremely useful. But once again, let's take it all in, alright? You give this function a position and it returns a probability of a particle being in that position. Okay, so if we imagine a line, and then we can assume that particle can be anywhere on that line. So if we want to figure out where the particle is, then we sample this position, we input in the equation, and we check, oh my goodness, the particle has a 25% chance of being in that position. We take another one, we once again do this exact same thing, and we see, oh my goodness, the particle has a 33% chance of being in that position. We sample another position, we input into the function, we get the output, and wow, the particle has a 10% chance of being in that position. That's how it works. Once again, we can connect the line, just like in the probability segment, and get this, the function describing the probability of being in any single place. Now, this all by itself is decently useful, because you can just take a position, input into the function, get the probability. But most of the time, we don't care about the probability of finding particle in any place. We most of the time care about finding the particle in between two places. Because, well, a single spot is not something you would normally do in physics. Normally, you would prefer finding particle between point A and point B. And if we rewind back to the probability segment, then you should know that the probability of finding the particle in between point A and point B would be just the area under the function in between point A and point B. That's probability. And oh boy, what is the operation that gives you the area under the function in between point A and point B? Well, that would be the integral. There we go. So we add in the integral to it, and we get an integral of psi complex conjugate psi dx. We're getting into the good stuff, because now we have to add an x to the mix. Why do we add an x? Well, this is actually one thing I haven't explained from probability, because it's just straight up too simple and too short to deserve an explanation. When we have this probability distribution, we have the area under it. If we add x into that spot, then what we get is we get the expected value. We just get the expected value from this probability. So if you actually input the x in there, what you get in return is the expected position of the particle. So if you were to sample this function over and over and over again, this would be the position that you would expect the particle to be. Okay? Now here's the thing. I know this is extremely complex. I know this is extremely difficult. I know there's a lot of things going on, a lot of operations, but we already achieved a pretty interesting result. Because what we got is the expected position of the particle, which is the quantum mechanical version of standard position. Yeah, that's the main difference between classical and quantum mechanics. In classical mechanics, when you have an object, you have the position of that object. So, you have a ball and then you have the exact position of that ball. You can say that the ball is 2 meters away from you, or 1 meter away from you, or maybe 1 meter to the left, 1 meter to the right. In quantum mechanics, you can't have that. The uncertainty principle disallows that, which basically means that you cannot have an exact position of something. Instead, the position is dependent on the probability, is dependent on the function describing the probability, and because of that, instead of working with values, we work with functions. Functions like these. So, there we go. Instead of position, we have this. Now, why do we have on the beginning of our example equation a derivative? D of x divided by d of t. Well, you should already be familiar with that very derivative, because we, once again, already made it once in this video. This derivative is just velocity. X is position, t is time. This is just position divided by time, or in other words, velocity. And that's what I find so amazing about classical mechanics versus quantum mechanics. Because even though these two things seem so much different, in reality, they're actually kind of the same thing. Not kind of, only exactly the same thing. The only difference is that in quantum mechanics, first of all, you don't work with values, only with functions, and second of all, you have to be way more precise. And because of that, you cannot really shorten your notation, because if we were to actually expand notation, then we should also use derivatives in classical mechanics. But in classical mechanics, it doesn't matter. Things are so large that you don't have to be really all that precise. So whenever people talk about quantum mechanics, about how complex it is, all you have to remember is that it works based on the same underlying rules as classical mechanics. It's very similar. It's still physics, right? It's still the same universe, same laws apply. The only difference is that you work with objects that are so small that you no longer can average the random outputs. You can no longer just average the noisiness. In real life, if the position of an object fluctuates by 1 nanometer, it's not that important. But in quantum mechanics, it is. That's why you can't afford to bind anything to a single value. You have to bind it to probability. You have to be precise. You can't just divide two numbers, you have to use derivatives. You have to make sure that the things do actually make sense, because otherwise, you will not even end up with a number that doesn't make any sense. You will end up with an entire equation that's just too large for quantum. And so there we go. That's what quantum mechanics is all about. I know that it's still pretty complicated, it's still pretty complex. I haven't explained it perfectly, but all I wanted to show you is that even though the notation is scary, the idea behind it isn't. This is just velocity. As scary and terrifying as it looks, it's just velocity. And that is it. And there we go. In a little bit of an hour, we went from addition to quantum mechanics. Yeah, I know that the explanation was lacking a bit in some areas, and I'm certain that many quantum physicists will yell at me, but you try explaining quantum mechanics from addition to quantum mechanics in a little bit over an hour. I know, I still haven't edited it all. Now, this was a massive video, and even though the final explanation might have been a bit lacking, I feel like I still deserve an ad segment. I haven't done those. Why? So first, let's start the most important thing, which is charity. Do you like charity? I like charity a lot, and because of that, I started my own charity gathering thing called Slice of Pie. Link in the description, https://makeit.wtf/charity/ where you can go donate to my new charity. Right now we're collecting for DBS Lions, and get a slice of this wonderful pie for yourself. It's a lot of fun. I myself already have donated $675 and will keep on donating even more. It's a lot of fun. You can get a slice of this pie. Tefta and Ali already donated, and they have their own slice of pie. Also, we also got some anonymous donations, so Anonymous also has a slice of pie. I would really recommend it. It's a lot of fun. How could you know about this slice of pie charity? Well, maybe from my live streams, because I stream every single day. Series of live streams called Charity Checkups, which I stream for charity, DBS Alliance, https://makeit.wtf/charity/. I'm sorry, the last explanation took like 4 takes or 5 takes to get through, so I'm a bit flabbergasted. In the end, it wasn't all that great. So would you like a better explanation? Well, how about you go to my second scientific channel called Make It Research, where I upload videos which aren't all about animations, manimations and flashy graphics, but more about just the message behind them. Just about the research, just about the information. Over there I will explain the quantum mechanical function, this quantum mechanical equation again, this time better, this time more calmly, this time with paint so I can actually draw my points. I would recommend, if you still have some doubts about the final explanation, I would recommend going over there. But if you're not, that's fun. But what if you're not into science? What if you're into gaming? Then, oh boy, you're in luck. I would really recommend you check out my fourth channel called MKT Charity Streams, where I, first of all, I stream on Twitch, but also I stream on YouTube. It's the same thing. I would recommend Twitch because my streams on Twitch have a little bit higher quality. Second of all, I upload a lot of shorts as clips from my stream, and third of all, I also upload videos. Extremely highly edited videos from these live streams once again, and they're pretty fun. Don't worry about it. I'm set. Okay! Guys, don't ring the bell, okay? I think there might be a monster inside. So I really recommend you go check it out. But oh wait, what if you don't like science or gaming? Well then, maybe you like cinematic stuff on my other channel called Make It Movies, where I upload cinematic stuff. We can go and check out the cinematic things, like for example the skip, which is great, or another video which once again will be coming out soon in a couple of days. There we go. But oh wait, what if you don't like any of these 5 channels? Well then, maybe you like the backstage from them, or the backstage in general on my 6th channel. I have 6 channels, alright? I am mentally ill. Yeah, that's the channel for either backstage, announcements and all the other things. I just have a lot of work to do for all of these channels, for live streams, for this video. If you'd like to support me, then I would really recommend my Patreon, where you can go donate some money to me and get some lovely perks in return. Or maybe my Discord server, we can go and chat with me. We can have a laugh, have a crack, we can talk about medicine, rant about random pop culture things, or maybe just share a fun piece of trivia from some scientific field or something. It's a lot of fun, I would really recommend. And I think that's it when it comes to the ad segment. I think these are all the things that I had to advertise. Which means now we can go to my favorite part of the video ending process, which is thanking people. Because I have a lot of people to thank. Like for example, Tefta. I mean, do I even need to say this? It's obviously I'm gonna thank Tefta. Tefta is like the sole reason for why my channel still even exists. My only Patreon supporter who supported me for such a... Well, the fact that Tefta is a Patreon supporter is actually one of the most minor reasons for why is the sole reason that this channel still exists. But just thank you, Tefta. I'm not gonna sit here and list the reasons for 30 minutes. I could. That would be a good video. Second of all, Ali, thank you for being entertaining on my live streams, because Lord knows I'm not. Okay, I may be bad at this, but it should be said, I really appreciate all of you, because I couldn't do it without you. Yeah, my live streams would absolutely suck if it wasn't for Ali. I would just... Even I would hate them. Then we have Soda, because all of the music in this video actually came from Soda KC. You can go check out their channel on YouTube too. They make amazing music, which I shamelessly steal with permission. Like, for example, my favorite, Iced Over, or maybe Rush, or maybe 1, 2, 3, or maybe Symmetric Storm, or maybe The Road Ahead, or maybe the Sanded Shores. I remember those still. And also is responsible for creating my channel theme, the theme 2. Thank you, Soda, for, well, all of this, obviously. I just said it, obviously. Then we'll keep on going to Hatake Hunt Elliot. Thank you, lads, for talking with me, because I'm actually kind of lonely. And then there's obviously more, like Stick, like A Mind to Think. But I should get around to finally finishing this video, actually. And you all know that I love you, but I still want to add you to the end of this video. I still want to add you all to the end of this video, just to make sure that you understand how much I appreciate your feedback and the fact that you're actually watching it, the fact that you're liking them. I really appreciate it a lot, because without you, I really wouldn't be able to do anything. And I feel like just thanking you on Discord or doing live streams or whilst chatting, I don't think that's enough. I think you deserve a portion of this video just dedicated to you, because you're the reason for I made them. So thank you all so much. Now, yeah, the theme 3 is finally kicking in, which means I should wrap it up, end the video with the standard saying, the standard thing I say, which is thank you all so much for watching, and have a great day. Bye!